Perseverance is the name of a new rover that landed successfully on Mars, and a location where there was probably previous water, and it's searching for evidence of past life. So we're excited to see more images come from that. I'll show you some once more come out. But anyways, this is what our current understanding is, something like this. The history of water on Mars is, remember, the solar system is around 5 billion years old. So maybe 4 billion years ago, shortly after the solar system had settled down after the heavy bombardment, late heavy bombardment around 4 billion years ago, Mars had vast oceans, or at the very least, very vast lakes. And the evidence seems to suggest that it pretty much dried up by about 1 to 2 billion years ago. So it's a kind of a fascinating story why this happened, and it relates to kind of the subject of a lot of this last lecture, which was, right, the fact that larger planets hold on to their heat longer than smaller planets to cool off. It has consequences. So it means that Mars now is geologically dead, whereas it wasn't in the past. And that has consequences for its magnetic field. And the magnetic field, as we'll see, shields and protects Mars as well as Earth from the solar wind. Okay, so the way Mars lost its water was through the fact that water vapor enters the atmosphere. Okay, so let's talk a little bit about atmospheres of these terrestrial planets as a way of understanding a number of things, including how Mars lost its water. So this is kind of one diagram that's maybe a little bit technical, but it contains a lot of interesting information. What it shows is what's called the escape velocity, or different types of molecules that might be in an atmosphere. What is the escape velocity? It's how fast it has to go in order to totally leave a planet's gravity. So if you imagine standing on the surface of the Earth, you can toss a ball up, but it doesn't escape, right? It falls back down, right? But you can imagine there's some velocity that if you could throw a ball that fast, it would just leave Earth entirely. And it's the same true for molecules, whether it's a water molecule, oxygen, nitrogen. It turns out that hydrogen and helium on Earth, the two lightest atoms, at Earth temperatures, they're moving faster than the escape velocity on it. Okay, and so they leave Earth's atmosphere. They just happily fly away. So if you pop a helium balloon, that helium eventually just leaves the Earth. And so that's shown in this diagram, where on the x-axis is temperature, because the higher the temperature of a gas, the faster the molecules are moving, so the easier they can escape. Okay? Now on the y-axis is basically how big the planet is, right? The escape velocity is going to be higher. It's harder to leave a big planet like Jupiter than it is a small planet like Mercury. Okay? So here's Earth, for example. Earth, at Earth temperatures and in Earth gravity, hydrogen and helium will just float away. Okay, but everything else can stay in Earth's atmosphere. Okay, on the other hand, really big planets like Jupiter and Saturn and Neptune and Uranus, which we'll talk about soon, these gas giant planets, these can hold on to hydrogen and helium. They can hold on to all of the gases because they have such strong gravity and they're cold. Okay, on the other hand, there's planets like Mercury or the Moon that have such low gravity that they can't hold on to hydrogen, helium. They can't hold on to water. They can't hold on to oxygen or nitrogen. And that's why they don't have atmospheres. Okay? They don't have atmospheres because almost all types of molecules just float away. Mars is kind of in the middle ground. Okay? Mars is it's not as big as Earth. It's not as small as Mercury. So it's kind of in the middle. And Mars is in a situation where it's perilously close to losing its water. Okay, water, oxygen, nitrogen, and stuff kind of wants to float away, but it's a close call. And this is ultimately the origin of why Mars had water and now it doesn't have water. Okay? Water vapor is something that in Mars' atmosphere, along with oxygen and nitrogen, doesn't stay around very long. but it's a very close call. Okay, and let's look, by the way, at the composition of all of the atmospheres of the terrestrial planets. One thing that's interesting, that's kind of a callback to when we talk about photosynthesis on Earth, is that they're all mostly carbon dioxide. Venus, Mars, original Earth, mostly carbon dioxide. Okay, Earth is special. I'm sorry, the original Earth, but Earth is special because it's changed, right? We had these photosynthetic organisms that removed a lot of carbon dioxide and replaced it with oxygen. So that's why, the remaining thing, the next most abundant besides carbon dioxide, is nitrogen. So that's why we see so much nitrogen in our atmosphere. And so Earth's atmosphere is mostly nitrogen and oxygen, and the CO2 was originally there. So this is what we see on Mars is now mostly CO2. Now, okay, but it has a very thin atmosphere because it can't hold on to much because its gravity is not as strong. As kind of a checkup here, right? I want you to know which has the most atmosphere, which the least in terms of the terrestrial world. Venus, I hope you remember, has the most substantial atmosphere. Not only is it more substantial than Earth's, but the pressure is 90 times.
So dirty.
Because it has such a thick atmosphere.
No.
That's also why it has such a big greenhouse effect.
No.
A lot of CO2, but also just
Bad.
a lot of
That's
its
why
atmosphere
we
is
said
thick.
email.
On the other hand, Mercury has the least substantial atmosphere. Okay. Right. Moon and Mercury both have hardly any atmospheres, but the Moon isn't on this list. Okay, so I won't try to trick you like this. But Mercury is a very small planet, doesn't have much gravity, can't hold on to an atmosphere. Now, the atmosphere is important. I mean, it has a number of effects. It can protect from radiation. We've talked, and we'll talk some more about the ozone layer. It helps protect us from ultraviolet rays that will give us like skin cancer, for example. The greenhouse effect, I'll talk a lot about that in a second when I talk about climate change. But an atmosphere causes the greenhouse effect. It can warm a planet, like how Venus is much hotter day and night than Mercury, even though it's further away from the sun than Mercury. Erosion, right? If you have an atmosphere, you can erode, smooth out all of those meteorites. So you have glaciation, that's ice that's moving over the surface and kind of smooth things out. You have rivers and wind, erosion. The radiation penetration here is the kind of opposite of radiation protection. I showed this picture before, but up on the top tells you which types of radiation penetrate the Earth's atmosphere. So, for example, the atmosphere allows radio waves, visible light through, but the atmosphere protects us. It protects us from ultraviolet, X-rays, gamma rays. Okay, it also protects us. It's not important that it protects. It's not a protection in this case, but it stops microwaves. The greenhouse gases, I'm going to go into this more in a second, but as a brief overview, what is a greenhouse gas? Okay, a greenhouse gas is a gas that absorbs infrared light. Now, infrared is important when it comes to heat, because remember how we talked about how all warm objects emit light. Okay, you and me, we're all emitting light right now, but we're emitting light that is invisible to our eyes, called infrared. Okay, and anything that's kind of not glowing red hot is mostly emitting infrared. And that's why we associate it with warmth. Greenhouse gases are gases that absorb infrared light. So when the Earth is trying to re-radiate its warmth back out into space, if you have an atmosphere filled with greenhouse gases, they absorb that light and prevent it from escaping. The main greenhouse gases are water vapor, okay, carbon dioxide, methane, and ozone. Okay, ozone, it's a small percentage, and we kind of like ozone because it also protects us from ultraviolet radiation. So we're usually not worried about ozone as a greenhouse gas. But water vapor, carbon dioxide, and methane, they are the main greenhouse gases. You can kind of see if you do look at the spectrum of sunlight reaching the Earth's surface and where it gets absorbed by water versus CO2. So here, this is all in the infrared wavelengths of light. And you see in the blue is where the water is acting on those wavelengths of light as a absorber of infrared radiation. And in red, you see where the CO2 is. Now, you might think, right, so we're really worried as humans about the fact that we emit carbon dioxide and methane, these things associated with burning fossil fuels. Right? What about water vapor? Well, it's the strongest greenhouse gas. And we're not too worried about emitting water vapor, but we are worried about CO2 levels increasing the warmth of our atmosphere. But then because a warm atmosphere can absorb more water, that in turn leads to more water vapor, which is in turn a stronger greenhouse gas. So there's a kind of a feedback mechanism that makes, anytime you add, say, CO2 and methane, it also indirectly causes you to add more water vapor. Oops, keep doing that by accident. Okay, so I want you to know what a greenhouse gas is. It's a gas that absorbs infrared light, okay? And the Earth cools off by radiating infrared out into space. So if you have an atmosphere that absorbs infrared light, it's like a blanket that keeps the Earth warm. Now, going back to Mars, so actually the next lecture, which we're going to get to in a second, I'm going to talk all about climate change. But to end this lecture on the terrestrial planets aside from Earth, right, I wanted to explain how Mars lost its water. So remember, we talked about how Mars is smaller than Earth. It's not as small as Mercury or the Moon. So it's not totally geologically dead, or at least it wasn't geologically dead immediately after formation, but it took a long time to slowly cool off. And so initially it had a hot liquid interior that had a dynamo that was caused it to have a magnetic field, okay? And that magnetic field, remember how I said that when we talked about the escape velocity of molecules in Mars's atmosphere, it's a close call. So Mars was on the verge of losing water over billions of years. Maybe slowly it would lose a little bit of water. But the big difference is that its magnetic field initially protected it from the solar wind, which would come in and break apart water into oxygen and hydrogen. Right? Water is H2O. And if you knock it with a ray from the solar wind hitting the atmosphere, it can knock apart the oxygen and the hydrogen. The oxygen's heavy, so it sinks down and it hugs the planet because it has a oxygen is a heavy molecule, so it's unlike helium, it doesn't float away. But hydrogen that's left behind when you break apart H2O does float away. And so that had the result, after Mars's magnetic field started to die away, it stopped protecting it from the solar wind. And so this happened. The water in the atmosphere slowly kept getting broken apart. The hydrogen floated away, leaving only oxygen around. And that explains why Mars is red, okay? That oxygen rusted the surface of Mars. Okay? So slowly, over millions and millions of years, the water vapor in the atmosphere broke apart, the hydrogen floated away, and the oxygen rusted the surface of Mars red. And that's how we think over a few billion years after Mars cooled off to the point that it lost its dynamo, it lost its magnetic field, it started to lose water, and over several billion years, all of those giant lake beds dried up. Okay. And we actually can see this process still happening because Mars still has some water. Okay. Remember, we keep discovering bits of water on Mars, mostly beneath the surface, but it still has some water. This process is still happening. And we can use spectroscopy to actually look at that, what's in the atmosphere of Mars. So here's a picture of Mars, and on the right is a composite. This is just kind of looking at all the different reflected light from Mars. But if you break it into pieces, we've colored blue, the hydrogen, the light coming from hydrogen. Remember, we can identify these from the spectrum. In green is the light coming from oxygen. And then red is just the reflected sunlight from the surface, which looks red. Okay, but if you look here, water is being broken apart, the hydrogen is floating away, which you can see, and the oxygen hugs the surface of Mars. So you can actually see this process by which water is breaking apart. It's leaving because the hydrogen is leaving. And only thing that remains is oxygen. So it's continuing to lose its water, the small amount that it still has. So I'm here's hopefully a freebie, okay, for a poll question. Make sure you're paying attention. Why is Mars red? Maybe 5 more. Okay, I'm ending it. Okay, most people got this right, because as I just said, Mars's surface was rusted by oxygen, okay? That oxygen that you just saw on that last page is hugging the surface of Mars because the H2O, the water, got broken apart. The oxygen rusted the surface. That's why it's red, because rust is the color red.
Oh, okay, okay.
All right, any questions about our overview of the terrestrial planets, including Mars and how it lost its water? And keep in mind, if Mars had oceans of water in the past, then there's a good likelihood it has had at least life, because life developed on Earth pretty rapidly after it cooled down and after the late heavy bombardment ended. So at the same time that Mars had water, Earth had developed life. So it's not implausible to think that Mars also had life that we might be able to find a record of. So that's one of the main missions that Mars has been, that NASA has been engaged. Okay, then let's continue. So we've been in the middle of talking about giving a tour of our solar system. When you talk about the terrestrial planets, one of which is the Earth, we talked a little bit about stuff relating to climate change. And I think before moving on to the rest of the planets, the Jovian planets, we call them, or the gas giant planets that are different from the terrestrial planets, it's worth pausing and discussing something that's relevant, not just to life on Earth, but potentially life on other planets as well. And that's climate and how it depends on some of these factors we've just been talking about, such as the possible volcanism on a planet, such as the presence of greenhouse gases and so on. And it really affects, as we see in our own solar system, say with Venus and us, it has an extremely large import on whether life can exist on a planet. So as prerequisite, we need to understand a little bit about what keeps the Earth warm, and that's the sun, right? We've talked a bit about why the inside of the Earth is warm, but here we're talking about the surface of the Earth. What keeps the surface of the Earth warm is primarily the sun. Someone asked a question here. Someone's asking a question. It'd be easiest if you ask it in person. If life would be lived on Mars, how would that be possible to get there? keeping in mind the popular. Well, so I'll answer a question about Mars that someone asked. Mars is a great distance away, right? This is the main problem is we've shown in the 60s that we could get people to the moon. The problem with getting people to Mars is just that it's going to take a journey of something like a year. You have to talk about a long mission that requires substantial risk. Okay, so people being on a really long mission, confined into a tiny little capsule with enough food and water and oxygen. We basically have the technology to do it, but it's very risky. Probably the hardest thing is getting people back from Mars because once you get down on Mars, the gravity is stronger than on the moon. So you need a more substantial system getting off Mars. And again, I think we have the technology and there's people talking about doing it, but it would be a huge challenge. So it's the sort of thing, like if we wanted to invest a huge amount of money, we could do it.
Why are you here? Go away!
General attitude, we can talk about this more later in the course, but people's general attitude, and I share this attitude, that it's so much cheaper to send probes that don't have humans on than for our same, for the same money, we can get really cool videos and pictures without sending a human. So it's like, do we want one mission to Mars where we put humans on Mars, or do we want 100 missions where we send probes to all these other cool places in the solar system? Some of which could have life, which we'll talk about maybe next lecture, the fact that some of the moons of Jupiter may very well have life. They're really exciting places. So, okay, that's what I'll say about that for now. Getting back to the question of climate change, right? It's the sun that warms the surface of the Earth. So let's just briefly talk about that. So this is a distribution in yellow of the wavelengths of light hitting the Earth's surface from the sun. Well, actually, this is not even hitting the Earth's surface yet. This is if you put a satellite out above the Earth's atmosphere. In yellow is what it looks like. And gray is the theoretical curve you would expect from a map. And yellow is what we see, which is very similar. It's called the black body spectrum. Just like I explained before, right? If you heat up a light bulb or the sun or a human, we're all emitting a range of wavelengths of light. Humans are mostly emitting light in the infrared. But remember, if you heat up a fire poker, it starts to glow red. This is the infrared. If you heat it up more, it starts to glow some yellow too, and you hit it up more, it starts to glow green and blue, and then all together it looks white. But really, it's emitting.
What the heck? You out here?
We're seeing in the visible part of the spectrum. So the wavelength corresponds where this peak is to red through violet. But also it's emitting some shorter wavelengths. And also it's emitting a lot of longer wavelengths corresponding to infrared. And overall, if you take a square meter, the amount of light hitting like a satellite up above the atmosphere is about 1,300 watts per square meter. So it's like a toaster oven's worth of light from the sun. Now, that's a little bit modified when we include the fact that some of the light is absorbed by the atmosphere. So that's what this plot is showing. It's showing in red what actually makes it through the atmosphere. You have places where not as much makes it through the atmosphere when certain things absorb different wavelengths of light. But generally, you see the same basic distribution of light. You have ozone over here, removing a lot of the ultraviolet, but most of the visible light gets through and a lot of the infrared gets through. And overall, so here I've overlaid the kind of smooth theoretical curve of showing that distribution of wavelengths of light. And I've overlaid the visible rainbow spectrum here, showing that indeed, right, where the peak of light from the sun is indeed in the visible part of the spectrum. And to the left of violet here, to the right of infrared is, so the right of red is infrared. That's about a 50% of the light. And it's also worth pointing out that overall, so this number here, 1,300 watts per square meter, overall, on average, we receive about a quarter of that. And that's because we receive half on average because of day and night, right? Half of the time we're at night. So we're not just out in space.
Go on the room.
Having light hit us. Half of the time we're on the other side of the earth and it's dark. But also because the earth is curved. So the other reason is that you have a certain amount of light striking the earth, but being spread over a curved surface. And because that curved surface has an area that's larger, so you have the same amount of energy spreading out over a larger surface area than a curved planet. Overall, when you take that and the day-night cycle into account, about a quarter. So on average, like if you have solar panels, on average, about a quarter of those 1,300 watts. So 300 or 400 watts or so per square meter is what you can expect to receive from your solar panels. Of course, solar panels also are not perfectly efficient. Okay, so this is the light from the sun hitting the earth and warming the earth. Okay, this is what we're talking about. Now, I can make the same plot.
Mandy.
Remember, it's emitting light back out. Okay, and this is actually how the earth doesn't just keep heating up, right? The sun warms the earth, but then the earth is releasing light back. But it's what we call black body distribution is mostly in the infrared. It's not emitting visible light. It's not hot enough. So here we have that same type of plot from the earth shining back out into space, but the earth is much less hotter than the sun. So the peak is in the infrared, not in visible spectrum. But the cool thing is if we plot these both on the same plot, here we have the sunlight hitting the earth in gray on the left. It's at shorter wavelengths. That's why it's on the left of this plot. And it's mostly in the visible part of the spectrum, right? So I still have the rainbow overlaid here on the left. But then the earth in turn is re-radiating all of that energy back. Mostly in infrared.
Yeah.
And these are in perfect balance. This is why the earth stays about the same temperature. Because if you take the air
Go in the room.
is equal to the area of the space earth. The total amount of light emitted by the earth is equal to the amount received. So that means that the earth doesn't keep cooling down, it doesn't keep heating up, it stays at the same temperature. It was a very important concept. The earth, the energy budget of the earth is in perfect balance. The amount of energy received is the amount of energy given back. And then so with that in mind, okay, let's talk about what can affect how much energy is received or given back by the earth. Okay, one is how much light hits the earth. Okay, we would call that energy input to the earth. Look, the sun over time is brightening. Now, this is not relevant on human lifespans. Okay, the sun is about 5 billion years old, but in another billion years, it'll be significantly brighter. Okay, and that'll eventually be a problem, right? We won't be able to live on Earth probably much after a billion years from now because it'll start getting too hot because of the sun. Okay, but in our lifetimes, that's totally negligible. Okay, another factor is called the solar variation, which is an 11-year solar cycle. So every 11 years, the sun, and we'll talk about this in detail when we get to the sun, the sun's output changes by about 1,000th, about 0.1%, not enough to be important. Another that we know about is the fact that Earth's, remember we talked about how Earth's tilt changes? Also the eccentricity of the Earth's orbit changes from being a little bit more circular to oval over thousands of years. That has a small effect that we can actually measure in the historical record. These are called the Milankovitch cycles. So these are things we understand. Okay, these are energy input to the Earth that do change. The other and probably more important, at least in our lifetimes, is how much heat the Earth retains. In other words, how much of that heat can it get back out? And so this is, we can talk about reflection versus absorption, right? Like how much of the light from the sun is reflected back out into space, or how much is absorbed, heating up the Earth's surface. Okay, we'll talk about that. That's called albedo. And another is retention. Okay, this is the greenhouse effect. This is how much heat does the atmosphere hold on to, as opposed to let it escape back out into space. I'm going to go into some more detail about each of these, but are there any questions so far? So, first of all, I just do want to note that the sun does get brighter over time. So, again, it's about 5 billion years old. And in another billion years, it'll be 10% brighter, okay? And that'll be a problem. And eventually the sun will die in about another 5 billion years. But for now, don't worry about it. This is not something that in our lifetimes is going to be an important factor. We will talk about this general sort of progression when we talk about the sun and stars in detail later on in the course. Another thing that we will also talk about in detail when we talk about the sun is called the solar cycle. And this is really an interesting feature of the sun, that every 11 years it goes through a cycle where there's more or less sunspots. The sun is just overall a little bit more or less brighter. There's more solar flares or fewer solar flares. And you can actually see this by looking for the sunspots on the sun. But this, first of all, it goes back and forth every 11 years. So it's not something that affects anything over hundreds of years. It averages out. And also, it's just a pretty small effect, and we know about it. The Milankovitch cycles are a little bit more important than that. These are cycles that, on the scale of tens of thousands of years, that have to do with the Earth's tilt changing. So remember, the Earth's tilt changes between about 22 degrees to 24 degrees over about 40,000 year cycle. And that changes the extremity of the seasons. Okay. Another thing is over about a period of about 100,000 years, the Earth's orbit changes from being more circular to being a little bit less circular. So meaning it can sometimes get a little bit closer to the sun over a 100,000 year cycle. And also remember, the Earth's tilt doesn't always point towards the North Star. It's something that kind of processes around. And when we put all these things together, we have a really good understanding of this total solar eclipse. We understand how it affects the Earth over tens of thousands of years. Again, it's not very important, and it does kind of average out overall. But it's something that we keep in mind, and that we do see some evidence of it affecting Earth's climate historically. But the other things are Earth's ability to retain heat. And one of the important factors here is called albedo. Okay? You're probably familiar with the idea that things that are white tend to reflect light and keep you cool, but things that are dark absorb light and keep you warm, right? We call that albedo. So something that's dark has an albedo of 0. It's a perfect absorber. Bare soil is an example of a good absorber. It heats up, it warms up in the sun. Sand is less good. Sand is a little bit more reflective. But things like ice and snow are really good reflectors. Okay, ice and snow have high albedo. Okay, they reflect a lot of the sun's light right back out into space, keeping the Earth cool. Here's a map of the albedo along the Earth, where red is higher albedo, blue is lower albedo, and what you see is, like, for example, the sandy areas in northern Africa tend to have higher albedos, meaning reflecting more light. Also, a place where there's lots of ice, like northern Canada, Siberia, tend to have a higher albedo. They're reflecting lots of light back out in space. Okay? Places that have lots of trees and dirt, like you see here in North America or Europe, tend to have lower albedos and are warming up faster in the sunlight. And this has important effects because if the Earth is colder, it has lots of snow and ice, then it's going to keep the Earth cool, right? Because it's reflecting all that energy out into space, right? Whereas if that ice melts and it gets warmer, then the Earth is going to continue getting warmer because now everything has a lower albedo. It's absorbing more light and heating up more. Okay, so this is a potential runaway effect, right? If Earth loses its ice, it stays warmer than it had been before, and which in turn melts more ice, which keeps the Earth warmer. Okay, so this is one of these important effects called albedo. So if Earth had a higher albedo, if it's more reflective, what would happen to its temperature? It would go down, it would cool off, right? So more ice and snow on Earth, Earth stays cool, less ice and snow, it starts warming up, which in turn melts more ice and snow, which makes Earth warmer. So this is one of the worries when we talk about climate change. Okay, the other thing here is greenhouse gases, right? This is, we talked about a few minutes ago, water vapor is the most potent greenhouse gas. Next is carbon dioxide and methane. And here's another potential runaway effect. In other words, if we add carbon dioxide and methane to that, that will heat the atmosphere, right? But warm atmospheres can hold more water vapor. Okay? Humidity goes up in Florida because it's warmer, right, compared to here. Warm atmospheres hold more water vapor, which in turn is a greenhouse gas and makes the atmosphere even warmer, which in turn can hold more water vapor. And so, again, like albedo, it's a potentially runaway effect, right? Where if we start warming up the atmosphere, it'll start warming up, gets more greenhouse gases, and warms up more. So we have to be careful, right? That currently it's in a balance, but we're in a situation, as we'll talk about, where things are starting to change very rapidly. As a reminder, this is the composition of the Earth's atmosphere. It's mostly nitrogen, about 80% nitrogen, 20% oxygen, 1% argon, which is an inert gas, tiny, tiny fraction of CO2. Tiny, tiny fraction is CO2. But it's such a potent greenhouse gas that it's actually really, really important. Okay, and we have more than doubled the amount of CO2 since we've been around. Now, most of the planets originally had atmospheres with lots of CO2. Venus, Mars, the original Earth were all CO2. Venus is still all CO2. Mars is still all CO2, but it has a very thin atmosphere. But the original Earth had a lot of carbon. But remember, most of that carbon dioxide was removed after photosynthetic organisms converted it into carbon that was stored eventually underneath the Earth, right? It's now a fossil fuel, and kind of essentially burnt out the oxygen and filled the Earth's atmosphere with oxygen. So one thing that's important about this is, one, our atmosphere is radically different than it was originally. But another important thing is that we could put it right back, right? It's hugely different now because over hundreds of millions of years, we've taken carbon out of that and replaced it with oxygen. But we can dig up that carbon and burn it with oxygen to create that CO2. We can bring it right back out. Okay. Kind of converting our atmosphere back to what it was. We're not anywhere close yet, but the change is very, very rapid right now. As we'll see.
Go away.
And this has an enormous effect. So let's look. This is an interesting plot that'll show you just how big this effect is of both albedo and the greenhouse effect. Now, you don't see much effect of greenhouse effect, say, on Mercury. So it doesn't have an atmosphere. So let's skip right to Venus. So here's Venus. Now, if we didn't have to worry about albedo, if we didn't have to worry about greenhouse effect, it'd actually be what we call in the Goldilocks zone. It's about the right distance from the sun that it would be kind of like room temperature on Venus. It'd be nice. You could have liquid water. But if you include albedo, the fact that Venus has a pretty reflective surface, so it's a pretty reflective planet, then it would be really cold. It would be well below freezing. It would be much too cold for humans to enjoy. But what do we actually see? Venus is actually up here. This is what we observe. Venus is an incredibly hot, the hottest of all the planets, day and night, over 700 degrees Kelvin, hotter than your oven. And that's all because of the greenhouse effect. That's because it has an incredibly thick carbon dioxide atmosphere. If we move to Earth, Earth here is in much more delicate balance, much thinner atmosphere than Venus, but nonetheless it's important. So it's actually important to see just how extreme Venus is compared to Earth, because even on Earth, this is really, really important. So on Earth, if we didn't have greenhouse gases, we would be what you see in blue here. More than 10 degrees, I think.
That's how many.
Colder than we are now, and everything would freeze. Okay, Earth would turn into an ice ball if Earth didn't have the greenhouse effect. So the greenhouse effect is really important. It keeps the Earth just
Let's play, man. I go on the roof.
so that we have liquid water on Earth. We still have some ice, but
What's your playing this happy?
water, which is really good for life on Earth.
What?
That's entirely because of
I'm not just playing your tabby right now. Go get it. Oh. That's phone or tabby.
So just as some examples, is what I just was showing here. Between this
Because you're not big enough. Oh.
when the average temperature on Earth would be almost
Because I need it. You don't need it. You don't got no phones number.
and freezing, so more than 20 degrees below freezing.
So go play your tabby.
Almost 20 degrees below freezing. I'm getting my words mixed up. Which is really cold. The oceans would freeze. Okay, Earth would not be a pleasant place to live. Okay, so greenhouse effect is very important on Earth. We want some. Any questions before we talk a little bit about the history of climate on Earth as we understand? So we have the ability to use various methods we'll talk about to understand how the climate looked historically on Earth and to compare that to what's happening now. One thing to understand, right, is that the Earth's, right, because of plate tectonics, because the Earth is geologically active, you know, things have changed a lot over the years. So here's just 250 million years ago, the Earth, the continents were all in one giant squished together continent we call Pangea, right? And so the Earth's surface has been changing over hundreds of millions of years. We talked about that in the context of the carbon cycle. We'll talk again about that today. That's the fact that the Earth is geologically active is very important to Earth's climate. And so what we're talking about with the geologic carbon cycle as a consequence of Earth's geologic activity is that the seafloors are changing. Over hundreds of millions of years, the seafloors are completely renewed, because the reason why these continents are moving around, they're like floating around on the surface of the planet, is because the ocean floors are moving. Because underneath you have this magma, hot magma rising, and then in a convection pattern, cool magma descending, and that you have mid-ocean ridges where the seafloors are being created, and then they dip down at the edges of these plates. And that has the consequence of being able to remove CO2 from the atmosphere. So this is called the geologic carbon cycle, okay? So what happens is you have atmospheric CO2, okay? So you have CO2 in the atmosphere. It dissolves in rainwater. We call this acid rain when it's bad. So CO2 dissolves in rainwater, produces carbonic acid or acid rain. That rain then, because it's acid, it erodes minerals, calcium, magnesium, potassium, sodium, into the ocean, okay? Those minerals combine with this carbon and CO2.
Why did you change the icon? Huh?
Minerals.
Why did you change it?
So, for example, calcium carbon, calcium CaCO3. That's one of these
Why?
elementary rock minerals that forms on the ocean floor from carbon dioxide. And then the subduction from these moving plates, because the Earth is geologically active, carries it back beneath the Earth, down into the inside of the planet. Okay, so, and it's called a cycle because then that CO2 can come back out eventually because you have volcanoes, right? Eventually you have places where that, that stuff from millions of years ago gets carried back out in a volcano, which burps out lots of CO2. So over hundreds of millions of years, this has actually created a very steady CO2 concentration in the Earth's atmosphere. We call this the geologic carbon cycle. And it's really useful. So it's nice for us that it's happened to create a steady amount of greenhouse effect in our atmosphere that's about right for humans to live in. Now, before humans, what might have caused changes in the climate or changes in greenhouse gases, for example? Well, every once in a while you get a really big volcano, right? And so there's been at least two really large glaciations in Earth's history, one about 700 million years ago, one about 600 million years ago, that likely started when there was a really large volcanic eruption. That volcano spews ash, okay, into the atmosphere. The ash cools down the Earth's surface, okay? Now, remember, if the Earth's surface cools and produces ice and snow, that increases the albedo, and that further cools the Earth. And it's a runaway effect until the Earth becomes kind of a snowball. So we see these evidence in the geologic record for large glaciations extending down even into the tropics. But the volcano also put out lots of CO2. And so over a few million years after that, that CO2 does its work through the greenhouse effect to eventually heat the planet back up. And you get what might be an ice-free hothouse, meaning no ice, it's too hot. Okay, and remember, when there's no ice, then the albedo is lower and the planet stays warmer. Okay, and then the planet's going to stay too hot for another 100 million years until that geologic carbon cycle can slowly get the CO2 back out of the atmosphere, eventually cooling the Earth back down to the point that it starts to have glaciations again. So that is the scale of climate change that we do see in Earth's past. Natural climate change. And these cycles last tens to hundreds of millions of years, we see. And how do we understand, right, some of this stuff in Earth's geologic history? Well, here's an example of seeing these layers of sedimentary rock actually turned on their side, right? Over millions of years, Earth moves around, right? You have formation of mountains, and eventually you have, initially horizontal layers of sedimentary deposits, initially on an ocean floor, have now been kind of crumpled up into mountains and turned on their sides and exposed. And you can actually read back through history by looking at each of these stripes, okay? They tell a history where you're going back in time, right? Going back through these stripes, going back in time. And each one contains information about what the atmosphere was like, about what existed, right? You look at fossils and so on. And one of the main tools we use are so in these fossils that we look at, you had, say, oxygen being brought into this mineral or fossil of an organism that was breathing oxygen, say. Well, remember, there's isotopes of oxygen. There's lighter oxygen and heavier oxygen. And so one thing is, for example, heavier oxygen, oxygen 18, which is shown in the y-axis, is more or less prevalent if the atmosphere is hot or cold. Okay? And so we can use that as what we call a proxy for temperature. And so this is an example going back 500 million years, showing, and so for each change in one of these units of oxygen 18 corresponds to about 1 to 2 degrees Celsius change. So what we see is that over the last 500 million years, the Earth's temperature has changed by about plus or minus 2 degrees Celsius about. And it goes up and down, changing generally over tens of millions of years. Sometimes you have a volcano burps out a little bit more CO2 or a little ash cooling down or heating the Earth up. You have glaciations changing the albedo, right? These are the sort of factors that change Earth's temperature. But it's balanced, remember, because if the Earth gets too hot, typically over millions of years, eventually the geologic carbon cycle removes CO2, which cools the Earth back down. We can learn more over the last 400,000 years or so by looking at ice cores. You've probably heard about, like in Antarctica, there are kilometers thick of ice that have built up over hundreds of thousands of years. And you can drill down and measure little bubbles of atmosphere that are trapped in that ice. So you can measure like exactly what was in the Earth's atmosphere thousands and thousands of years ago in these ice cores. So for example, we can measure how much CO2 there was in the atmosphere going back 400,000 years. You see generally 4 major climate cycles. So here you see a lot of CO2, less CO2, more, less, more, less, more, less. So about 4 major cycles over 400,000 years we see. Here's methane. Methane is also a greenhouse gas, also showing that same cycle, more, less, more, less, more, less, more, less. And then here are our proxies for temperature. So this is the amount of, so here's the oxygen proxy, here's a hydrogen proxy, and here I'm just, it gets a little technical, but here is the reconstructed temperature in the middle here. And so what you see is when the CO2 level was high, when the methane was high, the temperature was high. And you see 4 temperature cycles. So high, low, high, low, high, low, high, low. Okay. And the thing to understand about this is that we have a pretty good idea that Earth's climate has changed in the past, right? It's not like when we talk about human-caused climate change, it's not like this is surprising. We all have seen evidence like this of climate changing in the past. And it's changed in cycles. It's gone up and down, typically on the order of, a few degrees. Okay. And it's taken, in each case, hundreds of thousands of years. Here is now going into shorter time. So here's going back the last 2,000 years. There's a couple things to note. So one thing to note is humans discovered fossil fuels and started the Industrial Revolution around here. Really, we started ramping things up in the mid-1800s or so. The other thing to note is that there were times in Earth's past where we thought Earth's climate had changed. For example, the medieval warm period. But as you see here, Earth's climate wasn't warm in this particular time. No, that was just in Europe. There's just a local change in temperature in a particular part of the Earth, but overall, the climate wasn't changing. What is real is that we've been, over the last few thousand years, Earth's climate has been cooling, okay? And we call this, in fact, part of this before the Industrial Revolution was called the Little Ice Age, because Earth's climate had been cooling for the last few thousand years, getting colder and colder, starting to see more glaciation. What we see is just
what time you go back?
Revolution developed, Earth's temperature skyrocketed, okay? Much, much faster than anything we've ever seen.
Yeah, I know that, but what time you go back to the Kinley? Let's go right now, your lunch break. What time you go back?
It's relatively flat. Earth's climate is changing.
12 what? Give me your iPad.
Skyrockets. And so it's not surprising because what are we doing? We're pumping CO2 into the atmosphere since the 1800s, and we'll see later graphs of that, right? It's kind of huge amount of CO2 that we're changing the atmosphere with. So let's talk about some of the things that that's affecting. So in our lifetimes, there's actually some pretty amazing evidence that you can just see through pictures. So here's a series of great glaciers. I'm going to show you a kind of a before and after pic. So here's 1899, and then from the same location, 2003. So that's about 100 years. That turned into this. Glacier is gone. Peterson Glacier, 1930, same location, looks like that. Muir Glacier, 1941. So this is now only 80 years, same location. Actually, that photo is taken only 60 years later, same location. You still see the glacier is still there. It's just retreated. Muir Glacier, 1890. Some people taking photos with giant chunks of ice, same location. Columbia Glacier. Now this is a much shorter change. 2009, just in 6 years, it went from this to this. Okay. So we're seeing very, very rapid change. And remember that this isn't, as this ice melts, it actually accelerates the change because ice has a high albedo, which helps cool the Earth. Okay, and we're seeing, so here's just a bunch of pictures showing kind of before and after, just change in less than a decade. So left and right are showing you major changes just in the last decade. So we're not just seeing glaciers retreat, we're seeing average Arctic sea ice retreat. So
you were supposed to
the
go
last
back.
few decades, basically what we see is in September,
You're not go back?
ice on average is slowly.
So
Again,
did you have the class at the 12, 11, 15 to 12?
the main thing here is just that it has a high
After you're moving? So you go back.
I was at my classroom the whole time, but
less reflectivity.
You go back at 1:30.
Okay, now we have climate models, and here's just a climate model, or a number of models in various shades of blue, showing since the 1950s what we expected as the extent of Arctic sea ice, and the observations match the models. The models aren't so bad. You see in red what we actually observe. In fact, what we observe is a little bit worse than what the models have been predicting. And essentially what all the models predict is that in another, in your lifetimes, in another 50 years or so, it'll be close to zero Arctic sea ice. Okay, here's a graph of mean global sea level since 1995. So this is recent, right? I'm not going back thousands of years. This is just since 1995. The sea level is just increasing at a very, very steady pace. Okay, and what you see is just over the last 20 years, it's increased by about 10 centimeters. This is over the next 100 years, it's going to be a major global problem. I'll show some more projections in a minute, but I guess I'll just say for a second, right? There's already places. Well, I'll say this: that places that humans have built their largest cities are usually on coastlines, right? Historically, this is for a lot of reasons. One thing is that they're ports, right? They can bring in goods on the sea to the coasts. So major cities, right? Think of New York, right? New York City in the United States are on the coastlines, often at very low sea level, right? And of course, this isn't, this is even more of a problem not in the first world, where there's all sorts of island nations, places in the Pacific, for example, that are very low lying, where even a meter change of sea level will be catastrophic. Okay, and that's what we're talking about happening in the next.
If you next time you go to class, tell your friend to class.
So, how do humans influence climate? So, it's acid rain. We talked about that in the context of the geologic carbon cycle. Acid rain erodes, right, minerals, so it erodes infrastructure, right, like buildings you'll see slowly eroding because of CO2 Right, it's the same acid that you get in cola. Right, cola is bad for you. The carbonic acid erodes minerals, but it also changes ecosystems. It messes up with the oceans, and plants, plant life, and animal life in the oceans because it becomes acidic. This actually has been cleaned up substantially due to, for example, in the United States, the Clean Air Act really did reduce acid rains. That's something that's really been positive since the 1960s. That air quality, in particular acid rain, has improved in the United States. Another is the ozone layer. I'll talk about this more in a second. CFCs. Now, if you ever had to buy an air conditioning, they used to be made with a type of refrigerant that damaged the ozone layer. But the 1989 Montreal Protocol phased that out. And pretty much every major nation on Earth agreed, because it was only slightly more expensive, to change to different refrigerants. And so now if you buy an air conditioner, it'll always have a different refrigerant. This happened to me. I had to replace my AC, and the old one had the old refrigerant, and when I replaced it with had the new refrigerant. Okay, fossil fuel use, right? All that carbon-containing stuff, we burn it with oxygen, it turns into CO2. That produces greenhouse gas, also methane. Anywhere you use fossil fuels, you're talking about CO2 produced, but also methane. Okay, and so I'm not going to go into, of course, the fact that we're driving species to extinction, but I'm going to focus here just on the fact that temperature is changing due to the greenhouse effect and all of that, the consequences that come from that. So I think one thing that's important as a citizen is to realize that we're
You're
not
not going
totally
to class, Enoch?
quotes like this. To say who said the quote, so a politician is still around.
Class, come out and get the stupid iPad.
I said that in the speech. We can pass a bunch of laws that will destroy our economy.
Take a friend now. Class now.
Because, for example, there are other countries.
Give him his MacBook to a pencil. MacBook
And then
pencil.
like a week.
Countries
I told you to tell him to go to class. What the heck?
I did.
Pencil.
America is a country, not a planet.
Pencil.
We can pass a bunch of laws or executive priorities that will do nothing to change the climate, but will devastate our economy. And so this is a common sentiment you see. So now I'm talking. This is a common sentiment you see, which is that, hey, what's the point if the U.S. drops out of the Paris Climate Accord? It doesn't matter, because it doesn't matter what we do. You're still going to have China and India not playing fair, and they'll be doing most of the damage. But of course, this isn't true. In fact, this is exactly the sort of thing that we've dealt with before. And for example, with CFCs, the Montreal Protocol was exactly addressing this sort of problem. In that case was the ozone hole. We all just agreed that we had something similar to the Paris Accord, where we agreed to start phasing out CFCs. And what did it do? It started repairing the ozone hole. Okay, so here you see 1989, when the protocol went into effect, nations started abiding by it, and the ozone hole area has since flattened out and actually started getting smaller again. And I guess the main thing here with greenhouse gases is mostly CO2. And we can measure this. It's actually something really easy to measure.
Aren't you supposed to go to class? It's 12:30, Laura. You're in class, right?
Mauna Loa Observatory. It's in Hawaii. Right, so it's
That's
far
not
away
class?
from big polluting centers out in the middle of the ocean, measuring the atmosphere, and get these beautiful, beautiful plots. So this shows the amount of CO2 in our atmosphere measured at Mauna Loa since 1960. And look at this plot. So this is what's called an exponential curve, first of all, and that if you follow the average trend, which is shown in blue, it's the CO2 in the atmosphere is increasing exponentially. We just passed recently a major kind of number, 400 parts per million CO2. It just blew right by it. But for a few days in the news, it's like a couple years ago, that was a big thing. But so as you see, not only is CO2 increasing, about 300 parts per million in 1960, now over 400 parts per million in 2020. But it's also increasing exponentially. You see this curve is not only going like a straight line, it's actually increasing faster and faster. You see interesting things. If you zoom in, you see how it's fluctuating back and forth, the red data points. So if you zoom in, you see an annual cycle that goes from January through January. And that's because the Earth is undergoes kind of it's like the Earth is alive. I mean, it's breathing. The Earth goes through a cycle where in different times of year, it absorbs more CO2 as plants grow, and algae absorbs CO2 from the atmosphere and so on due to seasons. Okay, so the Earth is undergoing increases and decreasing CO2 every season. Okay, it's going through this sort of respiration cycle, more or less. But it averages out so that if you just take the year average in blue, you see the steady increase.
Where's the school bus?
And another thing that's pretty easy is to measure global surface temperatures. This is really important, by the way, doing this for the globe, because it's pretty easy to get a confused picture just by looking at your local region, which, look, it can be really cold in Texas like it was this last week. But that doesn't mean the Earth is cold. That's just in Texas. Somewhere else on the Earth is a little bit warmer, if Texas is cold this year. So you have to measure the whole globe, and we've been doing that. We have satellites, for example, to measure temperature now across the entire globe. The NOAA, NASA's Goddard Institute for Space Studies, Climate Research Unit in UK, and what we see is since 1975, the rate of global warming has been about 0.15 to 0.2 degrees centigrade per decade. So here is a picture this is from the NOAA, National Center for Environmental Information. Oh, that's the NCEI. And what you see is what's called the global temperature anomaly, meaning you set some arbitrary baseline of 0 based on how it was, 2,000 years ago, and you see that the temperature has been increasing. And not only is it increasing, again, it's this exponential pattern. So it's not just increasing linearly, its rate of increase is getting faster and faster, which actually matches, go back, it matches this plot, the CO2 that's an exponential curve. Here's from NASA, so you see the exact same thing from other agencies. So NOAA, NASA, and so what does this mean? 0.15 to 0.2 degrees per decade. So what does that mean? In a decade, right? In a decade, or say in 100 years, what is that? In 100 years, you're going to have 1 to 2 degrees change. So here's, again, should hopefully be a freebie for your poll question. So at the current rate, in the next century, the average global temperature will decreasing, is it increasing or remaining the same, and how much?
Mm.
Give you 5 more seconds. Okay. So most people got this right. I'm glad. No one should have gotten this wrong. So yes, at the current rate, first of all, temperatures are increasing. It's global warming, not global cooling at the moment. And it's increasing at about 1 to 2 degrees per 100 years. Degrees C right here. In Fahrenheit, that's more like 3 to 4 degrees. Okay, and that has consequences. So first of all, it's important to try to extrapolate in the future, 100 years or so. And great, that's what I just gave was at the current rate. The thing is, the rate is increasing currently. So it's important if we want to extrapolate, we need to understand how much emissions we're going to be having in the next 20, 30 years, right? Our human population is increasing. Are we going to keep emitting more and more? Or are we going to increase our solar and our wind power and nuclear power and phase out carbon? Well, so there's a number of scenarios that are modeled, for example, by panel. This is the International Panel on Climate Change here. Extrapolating using various models. A high growth model in red would be the least optimistic. If high growth, meaning, okay, all of these emerging economies, China and India, have high growth, burning lots of fossil fuels. It's unfortunately what may well happen. Or shown in orange, like if we somehow manage to not emit any more CO2 except remain at our current rate, which probably is not going to happen. So we can model out these various scenarios, and they correspond to different levels of warming, shown here, and consequently different levels of, for example, sea level rise. So here, for example, is the sea level that we've seen rise since 1992. As you see, it's very steadily increasing. By the way, it's important to check out, it was also from this International Panel on Climate Change report, sea level going back a few hundred years, you see it was pretty flat. Again, everything started changing very rapidly once we hit the Industrial Revolution, about 1850 or so. Suddenly, and what you see in different colors here are different measures of sea level rise, but they all pretty much agree to show very steady, if not exponentially increasing sea level rise. And so again, you can extrapolate based on different, optimistic or less optimistic scenarios. Probably the most, realistic scenario is closer now to this red scenario, which is about a meter of sea level rise in the next 100 years, which would be pretty catastrophic. So this is something that is actually going to start being important in all of our lifetimes. In the next 1 or 2 decades, we're going to start seeing consequences of this as nations start to have to grapple with larger and larger floods when you have weather events, essentially. That's first how it starts, right? You start seeing things like we've seen in New Orleans, US, right? Yearly floods are going to get worse and worse. That's the first thing that'll be a problem. Sorry, I saw someone. I don't know what to do if someone's frozen at this point. So, okay, going back to climate change. So, I just have to get on, just talk for a moment about the fact that this is a politicized issue. It's complicated, right? When do you listen to experts? If you do, who do you listen to? You'll always hear, especially now with Twitter and stuff, you'll hear about people sounding very authoritative, talking about people are full of it, or how talking about how there's no good consensus, or that there's groupthink or something. But it's important to understand that these people, that anyone can have a platform like this. So there's often essentially crackpots that sound very confident in themselves all the time. People like radio hosts like to be very sure of themselves like this, that don't have any idea what they're talking about. If you want to get a pretty good idea about what scientists are thinking on a given issue, as a lay person, usually the best thing to do is look at the major organizations, get a sense for any scientific consensus. So I'm going to just list a few examples of major scientific academies and professional organizations, all of which that have put out statements basically affirming what their consensus is. This includes, and in all these cases, their consensus is that human-caused climate change is happening, and it's a real problem. It's the case of the American Astronomical Society, the American Chemical Society, the American Geophysical, American Institute of Physics, the American Physical Society, the Geological Society of America, National Academy of Science, the World Bank. Okay, basically, all the major organizations pretty much agree on this issue. It's not really a topic of dispute. And it's also just worth mentioning that if someone says something like, if there's someone disagreeing about this, so here's some polls of scientists, where 90+% of scientists all agree that global warming is real and happening, caused by humans. And you always get a few saying no, but it's worth pointing out that this is always true in any scientific question. If you ask scientists, any scientific question about anything, there will always be a few percent that disagree. And this is good. This is healthy. This shows that science is a real thing that has people arguing and disagreeing. Scientists hate to agree on anything. That's the norm, believe me. So yeah, okay. I'll end this lecture there, which is that be careful about this current information age, where anyone on the internet or on a radio or anything like that tells you very confidently about anything. They're usually full of it. But I guess I'll leave it there and ask if there are any questions. All right, if there are no questions, on Wednesday we'll start talking about the rest of our planets and our solar system. I'll see you then.
Thank you.
If you're stranded in a proper shelter this climate, frostbite and preserving your set fast, when the human body's temperature drops below 28 degrees Celsius, you will lose motor dexterity within minutes, become unconscious in less than 15 minutes, and die in less than 45 minutes. For this reason, I would be listening to the local weather forecast before coming out. The next morning, then you're ready for the drive to Bear Valley. I might scratch it up in the car and a glacial storm right on the back. It looks like we're back to run into the gas station. Weather forecast before going out. The next morning, then you're ready for the drive to Bear Valley. I might scratch it